Okay, so this is still section 3.5. So now we're going to look at some examples. Before we do that, there's one important theorem, one important property that we're going to use over and over again. Okay, so this property is the following, right? It says that if you have R, a positive rational number, right? So that could be a whole number like 3, it could be a fraction like 1/2 or 2/3, and C is any real number, then the limit as x approaches infinity of C divided by x to the R is equal to 0. All right? And furthermore, if x to the R is defined when x is negative, then you also have that the limit as x goes to negative infinity of C over x to the R is equal to 0. Okay? So what does that, right, what does that mean and how does that work? So let's look at first example. Suppose we want to take the limit as x approaches infinity of 7 divided by x. Okay, so what's the limit as x goes to infinity of 7 divided by x? Well, I mean, on one sense, you can just apply the theorem, but let's see if we can understand what we're doing here, right? Remember what it means as x is going to infinity. X is getting bigger and bigger and bigger. So the question is, what's happening with 7 over x, 7 divided by x, right? And maybe I shouldn't have picked 7, but that's, all right, that'll work here. So here's the idea, right? Let's just do it the old-fashioned way. Let's make a table, right? So let's plug in values of x, and I should do a vertical one, but too late. It's going to be horizontal, right? So what's big, right? Obviously 10 is not very big, but we could plug in 10, right? And so if you plug in 10, you just get 7 over 10, or 0.7, right? So let's get bigger. You can do 100 or 1,000, but let's make it a lot bigger. Let's make it 10,000, right? So you have 7 divided by 10,000, which is 0.0007. Did I have enough zeros? So let's see. It's 10, 100, 1,000, 10,000. Yep, I think I have the right number of zeros. And you can see that this is a fairly small number. So what happens if you plug in an even bigger number, like 1 million? Right? Well, you get 7 divided by 1 million. I think I have too many zeros here, right? 6 zeros, right? But as a decimal, I'll write it under here. As a decimal, that's just 0.000007, right? And you can see that's a fairly small number. So what's happening as x is getting bigger here, you can make it, say, 1 billion, 10 to the 9th. So 7 divided by a billion is just going to be 7 times 10 to the negative 9, which is an even tinier number, right? So what's the idea? These numbers are getting bigger, x's are getting bigger, but 7 divided by x seems to be getting smaller and smaller. They're getting close to 0, right? So I think a reasonable answer to this question is that this limit is 0. Okay? So, I mean, that doesn't prove this theorem here, but at least it shows that it's not wrong, right? We have our constant c is 7, and r, of course, in this case is just 1, right? X to the 1 is x. R 1 is a rational number, right? So that gives us a pretty good idea of what's going on here, right? If the numerator is just a number, a constant, and the denominator involves some power of x, well, as x gets bigger, the denominator gets bigger, but that means the fraction gets smaller, right? As the denominator gets bigger, like in this example here, 7 divided by 1 million is a very small number, right? And 7 divided by a billion is an even smaller number, and so on. 7 divided by a trillion is even smaller. So, yep, as the denominator gets bigger, the whole fraction gets smaller. It goes to 0, okay? So I think that sort of is a reasonable idea here. Again, it doesn't prove it, but we're not going to prove it. We're just going to use this fact because it's very useful, actually. We're looking at more examples. So let's look at a second example. Suppose we have the limit as x goes to, let's make it negative infinity. And let's just do 1 divided by the square root of x. Okay, so what would that limit be? All right, so first of all, let's think of the square root of x. Again, we didn't take the limit yet, so I'm going to copy limit down. Everyone has been great at continuing to write limit until the very end, until you actually take the limit. So this is 1 over, so c is 1. And what's r, right? So this is x to what power? So if you remember square roots have an index of 2. This is just x to the power 1/2, right? So here our r is just 1/2. But 1/2 is a rational number, so this should still qualify, right? Okay, so we could make a table here as well. We'll do it over here. So here's x, and here's 1 over the square root of x, right? And remember, here we're going to negative infinity, so this is backwards. 0 is way over here, right? So what happens when we plug in 0? Well, we get 1 over 0, which is undefined. So that doesn't help, right? So what happens if we plug in something like negative 10, which is not very big, but it's a start. We get 1 divided by the square root of negative 10. And if you remember, the square root of a negative number is imaginary, and well, that doesn't seem to help. So it doesn't matter how big you get here. If you plug in negative 10,000, you get 1 over the square root of negative 10,000, which is still imaginary. And so we're not going to count imaginary numbers here. For our purposes, you can't graph them, for example. They're not on the y-axis. So essentially, these are not in the domain of the square root function. And so that's the important key here. If this quantity, the x to the 1/2, the square root of x, is defined when x is negative, then the limit would be 0. So if you read this too carefully and you think, well, right, that this would have to be 0 according to this theorem, be careful. Read this carefully, right? The function, the square root of x, is not defined when x is negative. We know that because we get imaginary numbers, right? And so this is not equal to 0. In fact, we just have to give up and say that this limit does not exist, right? And not because it's infinity or negative infinity. It's just it just doesn't have a value. There is no y value here. There's no real y value. So so that's what could go wrong here, right? If the things like square roots or fourth roots are not defined when x is negative, or any function that's not defined when x is negative, right? If you might remember the natural log function from pre-calculus. This function has a domain of x greater than 0. In fact, that's the same domain as this. X has to be greater than 0 here. That's right. And so it doesn't make any sense to take the limit as x goes to negative infinity because it's not defined there, right? Okay. However, continuing with this example, let's take the same limit, but now going to positive infinity of 1 over the square root of x, right? So now we're going to reverse this, and here's x, and here's 1 over the square root of x. That's a terrible looking x. Let me try that again. 1 over square root of x, right? So a very similar table here, but now we're going to be using positive numbers like 10, right? So 1 over the square root of 10, I don't know, it's something like 0.2 or 0.3, but not very small, right? If we plug in 100, you just get, the square root of 100 is 10, so you just get 1 over 10, 0.1. If you plug in 10,000, you get 0.01. Excuse me. So yes, you can plug in bigger numbers, 10,000, 100,000. Let's do 1 million, and you get 0.001. So x is getting very, very much bigger here. X is going to infinity, And these numbers are getting small, but not very quickly, right? You need a lot more zeros for x than you get for y. However, 0.001, right? Eventually you get 0.0001 and so on. So these numbers are getting close to 0. So in fact, this limit is actually equal to 0, right? So if you're going to positive infinity, right, it almost doesn't matter what the r is here, right? This will always be 0. As long as the numerator is just a number, just a constant, right? If it involves a power of x, then that's a separate question, right? But if you're going to negative infinity, you have to be careful, right? Things like the square root is undefined there, or the logarithm is undefined. Again, that doesn't apply here, but, you know, any function with a domain that doesn't involve enough, you know, x going to negative infinity, then you just give up and say the limit does not exist for those. Okay, so I think we'll look at another example here. Let's make this example 4. Right? Suppose we have the limit as x goes to, let's keep it positive here, positive infinity. So yeah, we want to make it a little more challenging here. How about x cubed minus 4x all over 2x cubed plus 3x squared. Okay, so yeah, way more complicated than, you know, 7 over x or 1 over square root of x. But it is a rational expression, right? It is a rational function. And so we should be able to figure out the limit. Again, one way is to make a table. But at some point, that's going to get very, very cumbersome to do. It is kind of tedious, right, to have to plug in, right, a lot of values here to see the pattern. You know, in some cases, the pattern might be obvious. In other cases, it might not be, right? So rather than make a table, we're going to use this property up here, this theorem 310. Now, we can't use it directly because notice the numerator is not a constant. It's not c here, right? It's a function of x, right? So we can't really use this property directly. However, we can do a little bit of algebra here and maybe rewrite it in a form where we can use this property. Again, I erased the property, but it's up here, right? So notice what we need is the numerator to be a constant, and we need all the x's in the denominators. So obviously we have x in the denominator here, but we also have x in the numerator, and so that's not going to work. But so the way we're going to do this is we're going to look at the biggest power in the denominator. In this case, the biggest power in the denominator is 3. Obviously, that's also the same is true for the numerator, but that's a coincidence, right? In this problem, yes, the degrees of the numerator and denominator happen to be equal, but they don't have to be, right? It's certainly not for the first 3 examples here. The degree of the numerator for example 1 was 0. The degree of the denominator here is 1. Okay, so they don't have to be the same, but they just happen to be the same in this example here. So you take the 3, the biggest power in the denominator, and what we're going to do is multiply numerator and denominator by the same thing. So put parentheses around everything here. And in the numerator, I'm going to multiply not by x cubed, but 1 over x cubed, right? And the same in the denominator. So I'm just multiplying by 1, so I'm not going to, right, I can cancel these if I want. But the idea is to rewrite this expression in such a way that I'm getting all the exponents in the denominators. After all, right, that's what we're looking for here. We're looking for the x's to be downstairs in the denominators. And this should allow us to do that, right? So now what's our fraction going to look like here? So if I distribute this, x cubed, well, okay, let me write it out. X cubed divided by x cubed minus 4x divided by x cubed, right? And then do the same thing in the denominator. When you distribute this, you get 2x cubed divided by x cubed plus 3x squared divided by x cubed. Okay, so that's just expanding all this out, right? Distributing what's on the outside here. Okay, so our next step is to simplify all this, right? Obviously, x cubed divided by x cubed, that's just 1. So as our next step, again, we didn't take the limit yet. We'll do that later. This x cubed divided by x cubed, that's just 1, right? And 4x divided by x cubed, so one of the x's cancels. We still have a 4 in the numerator, but in the denominator, right, we have 2 more x's. So 1 minus 3 is x to the negative 2, or in the denominator, x to the positive 2. Right? And you do the same thing for the denominator here. 2x cubed divided by x cubed, obviously the x cubes just cancel, so this is just 2, plus 3x squared divided by x cubed is going to be 3 divided by x. Okay, so is everyone okay with that? That I'm just simplifying all this? All right, so now we can come back. Hang on to this thought for a second. We're going to come back to this property here. And if you notice, as long as the numerator is just a constant, the denominator is some power of x, and that's going to be true here, right? So here we have a constant c, which is just 4 in the numerator, divided by x to a power r. Here r is 2, right? Well, according to this theorem up here, that this limit has to approach 0. Right? So this approaches 0. And the same is going to be true here, right? 3 over x. C is 3. This is x to the r, where r is 1 in this case. But according to that same property, this also has to approach 0. Right? So what does that mean for the result here? Well, this is still going to be the limit as x approaches infinity of 1 minus 0 over 2 plus 0. But that's just 1/2, right? So the limit of 1/2 is 1/2. Now we can actually take the limit. So we get our answer. We get 1/2. So that's the, so I messed up the original problem here, but I can copy it down again. The original example was the limit as x approaches infinity of x cubed minus 4x all over 2x cubed plus 3x squared. Now we know through this calculation here that this limit is 1/2. Okay, so I hope that helps. Now, some of you, very clever, if you remember from pre-calculus, are like, well, I knew that already. I knew this was 1/2 because in pre-calculus you taught us that if you have the same power in the numerator and denominator, you just divide the leading coefficients. The leading coefficients here are 1 over 2. So according to our pre-calculus method here, if we want to find the horizontal asymptote, all we have to do is compare the degree of the numerator and the degree of the denominator. When they're the same, we just divide the leading coefficients. 1 over 2 is 1/2. Right? And that's fair enough. After all, when we're finding a limit, remember we're finding the horizontal asymptote. If we're finding the limit as x goes to infinity, I should say, we're finding the horizontal asymptote, right? So if you want the horizontal asymptote for the first example, it would just be y equals 0, right? For example 2, you also have a horizontal asymptote of y equals 0. Now remember, it doesn't have to be true that both the limit going to positive infinity and the limit going to negative infinity have to be the same value. In this case, 1 exists, 1 is 0, and 1 does not exist. But if you remember, for the horizontal asymptote, it's only one of these have to be true, right? One of these have to be a limit. And in fact, if you do have a limit here, let's say the limit is -6, then you have two different asymptotes, two different horizontal asymptotes. You have one y equals 0, and then you have the other y equals -6. But for example 2 and 3, right, we only have one horizontal asymptote, y equals 0. Okay, so in any event, going back to example 4, this function here, again, I keep messing it up, but this function here has a horizontal asymptote of y equals 1/2. So yes, that is the same that you would get if you just used the methods from pre-calculus, right? And I'm going to do another example showing you the same thing here. Just realize that the question wasn't what is the horizontal asymptote, the question is to find the limit. And if that's the question, I want you to calculate it algebraically, right, using this process here, right? And we'll do a couple others just so you get the hang of it, but that's the idea. This is how I want you to calculate these limits. All right, so I guess we're up to example 5. Hang on here. So example 5. So let's take the limit as x goes to, let's make it negative infinity now. yeah, let's do x squared minus 3 divided by 2x plus, I changed my mind. Let's make it, because we did 2 already, let's make it 4x minus 1. Okay, so we want to find this limit here. Okay, well, so we're going to do the same trick that we did in this problem. We multiply the numerator and denominator by the same thing, 1 over x to some power. So what is that power here? Is it going to be 1 over x squared? So remember, last time I said that you pick the biggest power in the denominator. The biggest power in the denominator here is not 2, it's x to the 1. Okay, so we're going to divide top and bottom by x to the 1. So I'm going to rewrite all this. I know it's a pain to rewrite it, but that's part of the process here. So we have x squared minus 3, I'll put it in parentheses, divided by 4x minus 1. Right? So what we're going to multiply top and bottom here by is 1 over x, not 1 over x squared. That won't quite work out right. But 1 over x to the 1, because 1 is the power in the denominator. The biggest power in the denominator, right? The degree of the denominator. Okay, so now distributing this to each term in the numerator. Right, still going to negative infinity. We're going to get x squared over x. And you can do this in your head, right? X squared divided by x is just x. Minus 3 divided by x. Right, so essentially I'm skipping this step up here. Right. Maybe I shouldn't in the second example, but all right. So I'm cutting corners here. Likewise, 4x divided by x is really just 4, because the x's cancel. Minus 1 times 1 over x is still 1 over x. Okay, so, right, so I multiplied this out and I simplified all at once. Right, so, and feel free to do that. You don't have to go step by step here, as I did in example 4. Okay, so now we can go back way up here. Sorry to make you dizzy here, but we're going to apply this same property. We have a number in the numerator and x in the denominator, right? So that's what we have here. Right, that's what we have here. C over x to the r. This is, c is 3, r is 1. So this has to approach 0. And likewise, 1 over x also has to approach 0 as x goes to negative infinity. Right, either infinity or negative infinity, right? Because this is going to be defined positive or negative infinity. There's no square roots here. Okay, so what does that bring us here? So that brings us to the limit as x goes to negative infinity of just x minus 0, right? X minus 0 over 4 minus 0, or just x over 4. X over 4, right? So what happens to x over 4 as x goes to negative infinity? Well, this, right, certainly does not go to 0. It doesn't go to 1/4, right? X is not 1 here. X is getting bigger and bigger, but in the negative direction. So if x is negative 1 million, right, this is going to be negative 1 million divided by 4, which is some big negative number. I think it's negative 250,000, right? And if x is a billion, then you get negative 250 million. So you're getting negative, really big numbers, right? So this is just going to negative infinity. Right? In other words, this limit actually does not exist because this does not approach any one particular number, right? It doesn't approach 1/2 or 7 or 0, right? It does not exist, right? The numbers get bigger and bigger in the negative direction. Okay, so you can say negative infinity or does not exist. Again, I would prefer negative infinity because that's a little more descriptive. Does not exist could mean many things, right? It could mean it approaches a positive infinity, it could approach negative infinity, or as in example 2 here, it just doesn't approach anything, right? It's not even defined for negative x. Right. So here it's defined, it's just that, you know, as x goes to negative infinity, x over 4 goes to negative infinity as well, just a lot slower than x does, right, by a factor of 1/4. So I hope that helps, right? So that's example 5. I think I'm going to do one more example for this video, and then I might make a separate video for more complicated examples. So yeah, so let me do one more example in this video. I'll call it example 6, and then the next video I'll revert back to example 1. So yeah, let's make this, I think, a little more challenging. All right, how about, oops, sorry. We'll take the limit as x goes to, we'll go back to positive infinity. Let's do the sine of 2x divided by 3x. Yeah, you can have trig functions as well, right? So we haven't seen that yet, at least for these types of limits, but we've had problems before with trig functions involving limits. So if x were approaching 0, I hope you know how to do that. We've done many of those in chapter 1. But here we're going to negative infinity, so that's a slightly different problem here, right? Okay, so what do we do here? So we have sine of 2x over 3x. So obviously the biggest power in the denominator is 1, x to the 1. But the numerator, the sine of 2x is not a constant. It's not c. So if I can go way back up here for a second, we can't apply this theorem directly because c is a number, right? Sine of 2x is not a number. It depends on x. You know, if you remember, sine wiggles back and forth like this, right? It's a terrible graph, but it's not a constant. That's the point, right? So we're going to have to be a little bit more clever here, right? Sine of 2x may not be a constant. However, and if I drew a better graph, I can do this a little better here. So here's the x-axis, here's the y-axis. Basically, the sine graph is bounded. It's between 1 and negative 1, right? So if you remember, or you may not remember, that the range of the sine function is between positive 1, so less than positive 1, and bigger than or equal to negative 1. Okay? And that's true regardless of whether it's sine x or sine of 2x or sine of 3x. So you can stick a 2 in here, and that doesn't affect the amplitude of the sine function, right? In this case, it's still 1 and negative 1, right? It has to do with the 1 in front here. There's an invisible 1 sine 2x, right? Okay. So how does that help us here? Well, for this problem, let me leave this up for now. We're going to use the fact that, right, the sine of 2x varies, but it's between negative 1 and positive 1, right? So this expression here, well, yeah, sine of 2x divided by 3x, this is going to vary between 1 over 3x and negative 1 over 3x. Okay? So maybe now you see where this is going. If I look at this, if I take the limit of this as x goes to infinity, this goes to 0, right? You have a constant in the numerator and x to the power 1 in the denominator, right? So that goes to 0. On the other hand, on the left here, we have another c. c is negative 1. Well, technically it's negative 1/3, right? C is 1/3 here, C is negative 1/3, but it's just a number, right? And you have x in the denominator, x to the power 1 in the denominator. So it's just a different C in this case, but this also goes to 0. So, right, if the right side goes to 0, the left side goes to 0, this middle here also has to go to 0, right? Why? It goes way back to chapter 1. This is the Squeeze Theorem, which we haven't used much until now. Squeeze Theorem. So if you remember what the Squeeze Theorem says, very briefly, let me remind you, if you have 3 functions, say f, g, and h, and they vary this way, right? So g is in the middle, f is less than g, and g is less than h, right? I'm going to run out of space here, so let me move this down a little. if you have the limit as x approaches c, or although c could be infinity here, so let's use infinity, of f of x, if this is some value L, and that happens to be the same as the limit as x goes to infinity of h of x, right? Then, because g is in between, that guarantees that the limit as x goes to infinity of g of x also has to be L. So what's our L in this case? Sorry for the sloppiness, but our L in this case here is 0. Because it's the same for f of x, which is the negative 1 over 3x, and the h of x is 1 over 3x, positive 1 over 3x. And the g of x is what's in the middle, the sine 2x over 3x. Well, that also has to go to 0. So by the squeeze theorem here, right, now we know that this limit, has to equal 0, right, because of the squeeze theorem. Okay, so yeah, this was a trickier one because, well, if you forgot the squeeze theorem, then there's really not much else you can do here. Obviously, you could also fall back on making a table. We've done that many times. So these are the y values. These are the x values. So you just plug in very big numbers like 1,000, 1,000,000, and see what happens. Effectively, you're going to get very small numbers here. I don't know exactly what, but, 0.00 something, 004 maybe. And then here you're going to get 0.000000. That's going to go on for a while, right? So as x goes to infinity, the y values just get smaller and smaller. They go to 0. Okay? And you might say, well, isn't that the same thing that you would get if you applied this theorem up here? Right? These limits go to 0 as long as the numerator is a constant. The problem is, right, this numerator here, the sine of 2x, was not a constant. So it does have the same effect, but you can't apply that theorem directly because this is not equal to c. Right? What saved us, however, was the fact that the sine function is bounded between -1 and 1. Right? That's way up here. That's this statement up here. And because it's bounded between -1 and 1, our c's were -1 and +1. And so because those limits both go to 0, that forces the middle to go to 0 by the squeeze theorem. So it's really the squeeze theorem that we had to use in addition to this original property up here. Right? We use this for our f and g. For our f and h. Right? Here f of x was this mess here, and the h of x was this mess here, the 1 over 3x, and the f of x was -1 over 3x. And the g of x, the g here, is what's in the middle. That's the sine of 2x over 3x. Okay, so I hope that helps. Again, I'll make another video and we'll do a couple more examples using this property here. But for now, I hope this gives you at least the idea of how to calculate limits going to infinity or -infinity.